Welcome back to another video. In this video, we're going to switch from focusing on convergence tests for series, and we're going to start studying what are called power series. Now, power series are a type of series, and of course, we can look at them as we've been looking at series in the past, but power series are a particular kind of series, and we're going to see that they have certain properties that make them ideal and fantastic for working with to approximate other functions, including the transcendental functions such as e to the x, natural log of x, sine of x, those things that we can't write down by just adding, subtracting, multiplying, dividing terms, raising them to powers, or taking roots. In other words, they're not algebraic. So what we want to start with today is we want to go ahead and define what a power series is. Now, if you have not taken the time to watch this video by 3 Blue, 1 Brown, I highly recommend that you go watch it first. It gives a great overview of how power series come about, and they explain a little bit about how they're developed and why they might be important. Once you've watched the video, come on back and let's take an in-depth view of what a power series is. The first thing we want to do, of course, is define a power series. So we're going to start with some terminology. So a power series is basically just another type of series. It's not geometric necessarily, but we're looking at a type of series that involves a variable. Now, we're not talking about the index variable, n or k. We're talking about another variable, such as x. When the variable is x, then all the terms in the series involve powers of x. So, for example, we can look at this series right here, which is a very basic power series, and it goes from n equals 0 to infinity. It has a series of constants on each term, c sub n, multiplied by powers of x to the nth. So this gives us c sub 0, x to the 0, c sub 1, x to the first, c sub 2, x squared, c sub 3, x cubed, blah, 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 forever and ever. Now we know that x to the 0 should be 1, provided that x is not 0. And so we get c sub 0 plus c1x plus c2x squared and so on. Well, in a weird kind of way, this is forming an infinite polynomial. Now, we love polynomials, as you know. They're our favorite class of functions. And why do we like polynomials so much? Well, because they're easy to work with, right? They're defined everywhere, they're differentiable everywhere, they're integrable everywhere, they're easy to take the derivative, easy to integrate, just easy overall to work with. Now, let's look at a more specific power series where all the coefficients c sub n are equal to 1. So when we're looking at that one right here, you can see that we've got this series from n equals 0 to infinity of x to the n. Since all of our coefficients, c sub n, are 1, this just gives us x to the 0 plus x to the 1 plus x squared plus x cubed plus x to the 4th and so on. And the first term, of course, would be 1, provided that x is not 0, or at least not yet. So we have 1 plus x squared plus x cubed plus x to the 4th, but it goes on forever. So it's like an infinite polynomial. And we call this a power series because we have powers on a new variable which does not depend on the index of the series. So the index is n, and this is the variable x. So x is raised to the n power, but x is not n. All right, now in looking at this particular series, and we can look at the representation of it over here, how do you get from one term to the next, to the next, to the next? Well, to get from 1 to x, I multiply by x, and to get from x to the first to x squared, I multiply by x. And so basically, well, gosh, this looks like a geometric series where you're multiplying by the same thing to get from one term to the next, to the next, to the next. And in fact, it is a geometric series where that common ratio there is just x. But x is now a variable whose value we don't know yet. So it's something that would be allowed to change. But we know by the convergence of geometric series that as long as that common ratio is strictly between -1 and 1, it will converge. In fact, we know what it converges to. It converges to a sub first, the first term in the series, divided by 1 minus the common ratio. But our common ratio in this particular series is x. And so our first term, of course, is 1. So a first is 1, and r, the common ratio, is x. So this infinite polynomial must converge to the function 1 over 1 minus x. Whoa! So we have a new representation for this rational function, 1 over 1 minus x, but it is only accurate as long as we're in that interval of convergence from -1 to 1. Now you may say, well, that's not so great. Well, it depends. If you're programming a computer or something else, this may be a really good way of doing it because polynomials are easy to compute on a computer. Let's now move on to the next part. So our goal, basically, when possible, is to represent series such as c to the n, x to the n in such a way that they represent or look like a geometric series, if possible. This is not always possible. A power series will always have x or x minus a raised to the nth power. So it's always going to have a variable raised to the index power. That's always going to be there. But we won't always be able to represent them as strictly geometric series. But when we can, that's the easiest way to go. So we want to do that. Now, we're going to first define what power series are more formally, and then we're going to show how to determine when a power series converges and when it diverges. Now, we've already talked about one example of a power series, and that was this one right here. And we know, in fact, that because it can be written in strictly geometric form, that it must converge, and that, in fact, it must converge to 1 over 1 minus x. So we know what this one converges to. So when we can represent it as a geometric series, then we already know what it will converge to, and we can put that in right here. Now, again, we're allowed to choose different values for x as long as they stay in that interval of convergence, that x between -1 and 1. So I could choose x to be -1/2, or I could choose x to be 2/3, or x to be 1/5. And then I could substitute that value in up here. I would get this infinite polynomial, but it's basically giving me the value of what I have down here. It's just another way to represent it. Now, this is one of our building block kind of functions, but we also want to consider ones that can't be written as geometric series. And we want some way of determining when these converge and in what interval they converge. So let's go ahead and define a power series more formally. So when we're looking at the definition of a power series, we'll start with the basic one, which is c sub n x to the n. This is just the basic one, but again, you may have some coefficients here that may change depending on which term you're in. So the constants may not always be the same thing. And then this is called a power series centered at 0. Why 0? Well, if x is 0, everything drops out except the first term, although we have a bit of a problem because technically, by the definition of this power series, the first term would have x to the 0, and that would give us 0 to the 0. But we're going to see that we're going to define that in a particular way for a power series to still make it work. So hold that thought for a minute. We also can write series in a more general form where it's not necessarily centered around 0. Instead, it's centered around some constant a. Now, a could be 0, but it doesn't have to be. In other words, the base of this exponential-like factor is x minus a. So you have c sub 0, x minus a to the 0th, which is 1. And then c1, x minus a to the first, c2, x minus a squared, and so forth. All right, now we would call this a power series centered at x equal a. And in fact, if you think about this one right here, we could rewrite it in such a way that it looks like the other one. So we could rewrite this one as the series from n equals 0 to infinity of c sub n x minus 0 raised to the nth power, and it would generate the same term. So you can see that this one can be written in this form. So this is a more general form. This is specific to ones that are centered at 0, but this is general. And of course, if we let a be 0, then it just becomes this, which is this. Now we let the c sub n represent the coefficient of the nth term of that sequence or series term. And then we need to deal with this x to the 0, all right? Because remember, when we're substituting in the original, if we look at this one again, we have c sub 0 x to the 0. Well, if x is 0, then I have 0 to the 0, which we know is indeterminate. So we have to deal with what's happening in that first term if we allow it to be the center. So if we allow it to be the center, what we're going to do is we're going to define for a power series x to the 0th to be 1 and x minus a to the 0th to be 1, even when x is equal to 0 for the first and x is equal to a for the second. Now, both of those would generate that indeterminate 0 to the 0 form, but we're going to define it so that it becomes the constant 1. And that way we can get around this indeterminate issue. Now, a definition is not something that can be proved. It's just something we say this is, therefore it is. So we made the definition so that we could work with these power series, even though we have this weird indeterminate thing happening on the first term. That gives us the following definition. So if we let, now that we've made that definition, that x minus a to the 0th power is going to be 1, even if a is x, then if we do let x be a, then the entire series becomes c sub 0 plus 0 plus 0 plus 0 plus 0. The only term that survives is the first one, because if we let x be a, then all the other ones, x minus a to the first, x minus a squared, x minus a to the third, become a minus a, which is 0 to the first, 0 to the second, 0 to the third, and so on. And so they disappear, and we end up with c sub 0. In other words, this value of the series, this infinite series, converges to c sub 0 when we allow x to be the center, which is a. Now, likewise, in the original power series, the more simple form, c sub n x to the n, centered at 0, if we let x be the center, which is 0, then the expression again degenerates into c sub 0 plus c1x plus c2x squared, c3x cubed. But if x is 0, then all the terms with x in it drop out. Remember, we defined x to the 0 to be 1, no matter what the value of x is, including 0 to the 0. We defined it that way. And that tells us that it also converges to that first coefficient, c sub 0. Both series then converge to their first coefficient, c sub 0, when we allow x to be the center of the series, all right? So that would be x equal to a in this case, and x equal to 0 in this case. And these are called the centers of a series. So let's define the center more formally. The value a is called the center of the series for the series c sub n x minus a quantity to the nth power. Why? Because if we allowed x to be a, then all the later terms other than the first will go to 0, and it will converge to c sub 0, the first coefficient. And for cx to the n, the center is 0 for the same reason. So we call those the center. Now, both of these are written in geometric form. We know that the ratio is x for the simpler one, and the common ratio is x minus a, the quantity, for the more complicated one. And we know that the simpler one will converge based on the rules for geometric series if the magnitude of x is less than 1. In other words, it's between -1 and 1. and it will diverge otherwise. So for the magnitude greater than or equal to 1. And by the same logic, that means that this more complicated form, the power series centered at A, must converge if that common ratio, x minus a's magnitude, is less than 1. In other words, x minus a is between -1 and 1, and otherwise it will diverge. Now, we know the power series, we know what they converge to when they're geometric, and these are geometric. So we know they'll converge to a first over 1 minus r, which becomes the function 1 over 1 minus x for the first one, and to a first 1 over 1 minus r, which becomes 1 over 1 minus quantity x minus a for the second one. So we're getting a representation for a function written in series form. Let's take a look at a couple of examples of what power series can look like, so you can see more complicated power series. So far, we've only looked at more simple power series, but now we want to look at more complicated ones. So for example, this is the power series from n equals 0 to infinity of x to the n over n factorial. And this becomes 1 plus x squared over 2 factorial plus x3 cubed over 3 factorial plus x to the 4th over 4 factorial, and so on. Now, there's no way to write this one in strictly geometric form because we have this factor in factorial in the denominator. So we can't pull that into the common ratio r. So it cannot be written as a strictly geometric series. So we're going to have to find another way to determine when this power series converges and over what interval. So when we're looking at this one, again, it's still a power series because we have a variable x raised to the index power. Let's take a look at this one over here. Now, this one over here is centered at 2 because the base of the exponential-like factor is x minus 2 quantity to the n. So it's centered at 2. But we do also have two other factors which depend upon n. We have the factor n plus 1, and we have the factor 3 to the nth power. Now, again, these can't be pulled in as part of that common ratio. It's not how we get from one to the next to the next. It's not a common ratio. So we can't write this in strictly geometric form. So again, we're going to have to find some other way of determining whether or not this power series centered at 2 converges and over what interval it might converge. So we need another technique to determine when they converge and over what interval. We know that the power series, no matter what it looks like, will converge to its first coefficient at its center. So we know that all power series at least converge at their center. None of them have the situation where they never converge. They all converge at least at their center. But it is possible that they converge maybe even over all real numbers, or maybe over some subset of the real numbers, right? And we want to find that interval of convergence. So now we want to take a look at this theorem, which talks about what are the possibilities for convergence. We're going to write it in the more generic form with center of A, but again, we could allow A to be 0, and that would center it at 0. So A could be 0 or not. So we have the power series C sub n x minus a quantity to the nth power. Now, one of 3 things happens. Either this series converges only at its center, x equal a, and it diverges everywhere else, right? And in this case, we know what it converges to. It'll converge to C sub 0, the first one. The series converges for all real numbers x, so over the entire real number line, or there's some subset of the real number line over which it converges. So there's some real number, uppercase R greater than 0, where as long as the common ratio x minus a is less than r in magnitude, that means it's between negative r and r, then we know it will converge. All right. So again, when you put an absolute value less than something, you're between the opposite of that value and the value, right? If it's a positive value. So it's between negative R and R. So let's write that down so that you're understanding what you have. Then we have something like this. So the question is then, what about at R and at negative R? Well, the question is it strictly less than, or could it be less than equal to? And the answer is, well, since it's not going to, the ones that are not strictly geometric, we'll have to find out. If it's strictly geometric, we know that its strict inequality is strictly less than. But the ones that aren't written as a strictly geometric series, you may have to check those endpoints individually. In other words, you may have to evaluate it at negative R and see if that series converges, and evaluate it at R and see if that series converges. All right, so we have three possibilities going on here. Let's do a little bit more definition. So we want to define the radius of convergence, that uppercase R. Let's suppose that the power series is converging for some value of uppercase R, so on some subset of the real number line. So as long as the magnitude of x minus a is less than R, then the series will converge, and otherwise it diverges. Well, then what we're talking about is we have this interval here that you can see in the picture down here, where you've got the center in the center of the interval of convergence. That's why it's called the center. So you have a minus r to the left and you have a plus r to the right. Because basically, when you have the magnitude of x minus a less than r, this part right here, then you can rewrite this as being between negative r and r. And we don't really know what happens at the two values. We don't really know if they're strictly less than or if they could be less than equal to on one or both sides. But we know we have that relationship, which means I can add the r to all, or add the a to all three parts. And this gives me a minus r less than x less than a plus r. And you'll see this down here in this particular image. So we have a minus r on the left and we have a plus r on the right. And we know that if we're inside that interval, then it definitely converges. We don't know what happens at a minus r. We don't know what happens at a plus r. We'll have to check those individually. But this does give me an interval that's 2r long, right? Because the distance from a to a minus r is length r. And the distance from a to a plus r is also length r. Now, if we think of the radius as being from the center to the edge of the interval, then we can call this length r the radius of the interval. And we call that the radius of convergence. So let's look back at the definition. This value, uppercase r, is called the radius of convergence, right? So it's the value around the center within which the power series will converge. And again, we'll have to check the endpoints specifically. Now, we call the interval from a minus r to a plus r the interval of convergence, and we often denote it with an italicized uppercase I. So you'll see this in the notes quite a bit, this uppercase I. Let's again consider those three possibilities for convergence that came out of that theorem, all right? So one possibility, of course, is that the series only converges at the center, A. Now, we could allow A to be 0, so we're including both of those cases. By definition, if it converges only at the center A, then we write that the interval of convergence is A. In other words, this is set notation that you see right here, where you have this curly bracket around A. The curly brackets are set notation, and that means that the only place it converges is at A. Now you can write it in interval form. It looks a little bizarre. You start at A and go to A, so it only includes a single point A. And that's a fine way of writing it as well. In this case, though, what are we talking about? Well, if we think about our picture up here again, if it's only converging at the center, then A minus R is at A and A plus R is at A. So R is essentially 0. So the radius of convergence in that particular case would be 0. All right, now let's look at the following figure. Let's see if we can get them on the same screen. So this is what we see in figure A down here at the bottom. So again, it's only converging at the center and it's diverging at all other real values on the number line. So it's only converging at the center. And when it converges at the center, again, we would say that the radius of convergence is 0. And we would say that the interval of convergence goes from A to A, or you can use set notation and put it in curly brackets. And that represents the single point A. All right, so that's one possibility. What about the second possibility? In the second case, we said that it is possible that the power series converges for all real numbers. And in that case, we'll say that the radius of convergence is infinity, and the interval of convergence is from negative infinity to infinity. In other words, it converges on the entire real number line. And this is shown in figure B. So when you're looking at figure B, again, we say that the radius of convergence, which is essentially half of the interval of convergence. So, but that goes to negative infinity, so it's infinity wide. And that goes to positive infinity, so it's infinity wide. That gives us the radius of convergence is infinity. And then we say the interval of convergence goes from negative infinity to infinity. That was the second possibility. The third possibility is the one that we had in the image up here, where we had some definite constant value, uppercase R greater than 0, and it converged between A minus R and A plus R without knowing exactly what happens at the endpoints. And that's what you see down here in this third situation, right? So we have convergence definitely on the open interval A minus R to A plus R. We don't know what happens at the endpoints. It may converge, it may not. Depends on whether it was allowed to be written in a strictly geometric, then it would be strict inequality, and the others you have to determine on a case-by-case basis. So you'll be checking lots of endpoints. Outside of that interval of convergence, it definitely diverges, right? So in this particular case, we have that the radius, well, is itself, right? So R is equal to R, which sounds kind of silly, but the interval is 2R wide, R on the left and R on the right. So there's some number for that. So for example, if it went from -2 to 2, the radius of convergence would be 2, because -2 to 2 is 4 wide and half of that is 2. And that would be from the center to the edge. Now, what about the interval of convergence? Well, the interval of convergence, again, we don't know what happens at these endpoints, A minus R and A plus R, and we have to determine that separately. Now, when we determine that separately, there are 4 possibilities. So let's take a look at the 4 possibilities. The 4 possibilities are, it doesn't converge at either endpoint, and this will definitely be the case if it's a geometric only type series, but it could also converge at only the left endpoint, A minus R. So this would be a square bracket, but it would be a round parentheses on the right because it doesn't converge on the right, or it could converge only at the right. So we'd have a square bracket on the right, but not on the left. And it can also converge at both endpoints. So we have square brackets at both. So we have 4 possibilities in that third situation when we have an interval of convergence between A minus R and A plus R. Now we want to think about how to determine convergence of a power series. So again, we've got some variable x or x minus a raised to the nth power, and we may have other factors that depend on n as well. If the power series can be written in strictly geometric form, where we have a common ratio to get from one term to the next, well, then we know what happens. In that case, we have the common ratio is either x or x minus a, and it will converge whenever the magnitude of each of those is less than 1. In that case, the factors of the sum n can be written in such a way that they represent a geometric series in the form of a single constant times some common ratio to the n, where r is x or x minus a, and it's raised to a power. And we don't know where it might start. It might start at 0, might start at 1, hard to say, but it's still geometric in form. In other words, there are no factors that depend on n that aren't a part of that common ratio. In these cases, since it's already geometric, we know when it converges, and we know what it converges to. Now, what if we don't have a series like that? What if we have one more like the examples of the power series that we saw right here, where we have this factor n factorial? So there's no way to multiply by the same ratio to get from one term to the next or the next, because the denominator is a factorial that is increasing with the subscript, increasing with n, the index. So what do we do in a case like this? It's not strictly geometric in nature. So if it's not strictly geometric in nature, then what we want to do is apply the ratio test. Now, why would we want to apply the ratio test? In this case, it's because the condition for convergence of the series using the ratio test or the root test is the same as the condition for a geometric series. For the ratio test or the root test, we're looking for rho, and rho has to be less than 1 in order to converge. Well, that's the same as the geometric series condition for convergence. And so we use the ratio test in order to test those particular power series that can't be written in solely geometric form. We use the test for absolute convergence with the absolute value bars, and this will give us the interval of convergence. It has the same condition that rho has to be less than 1 as the condition for a geometric. So remember again that rho for the ratio test is the limit as the index goes to infinity of a sub n plus 1 over a sub n, where a sub n is, of course, the term of the sequence on which the power series is built. Now, in this case, it is often what happens is that the limit is dependent only on the index of summation, which is usually either n or k. And because the limit only depends on n and not on x, which is our other variable, then anything that has x in it but does not have n in it as a factor can actually be factored out of the limit. So if we end up with an x squared inside of this limit multiplied by everything else, we can actually factor the x squared out of the limit, because the limit only depends on n, and x squared doesn't depend on n. Now, if it's x to the n, all bets are off, because then it does depend on n, so it can't come out of the limit. But if it's x or x squared or x cubed, it can come out of the limit because it doesn't depend upon n. So we'll see it can come out much like a constant does. Don't forget to check the endpoints for convergence when you're using the ratio test. We know what happens if it's written in strictly geometric form. Those are strict inequalities, but we don't know what happens with the ratio test. Remember that in that situation, it's inconclusive. So we have to check the endpoints for convergence. And you can't just check one, you have to check both. One might converge and the other one not, as we saw in the 4 possibilities above. Now we want to take a look at some examples. So let's take a look at some examples and see how to apply what we're doing. Now I've given you a hint on this one, and the hint is first determine if it can be written as a strictly geometric series with some common ratio that you multiply by to get from one term to the next, to the next, to the next. If we can write it in strictly geometric form, then we know when it will converge and we know what it converges to. So let's take a look at this one and see if that's even possible. So we can take our series n equals 0 to infinity of -1 to the n, x to the n over 5 to the n. And notice that all of these are raised to the nth power, and they're all multiplied or divided together. Well, then I could put all of them together with the nth power on the outside. So this could give me -x over 5 raised to the nth power. Now, again, x is a variable, but it's going to represent some constant number within the interval of convergence. So our job is to figure out what that interval of convergence is. Now notice that what's inside here, serving as r, does not depend upon n. And the n is only on the outside. So what's inside here does not depend on the index of summation n. And that means that this is written in strictly geometric form. It's a constant, which is 1, multiplied by a ratio r not dependent on n, raised to the nth power. So in this particular case, we know that it's strictly geometric. And that means that we know when it will converge. It will converge whenever the magnitude of -x over 5 is less than 1. Now, when we take the absolute values, we can drop the negative, and that would give me, of course, that the magnitude of x over 5 is less than 1. Now, 5 is a constant, it's not going to change. I can factor the 1/5 out, and that would give me 1/5 the magnitude of x less than 1. And then I can multiply both sides by 5 to get the magnitude of x less than 5. Now, if I'm looking at that, I've isolated the variable inside the absolute values, and now I can apply the definition of the absolute value less than a number to say that this then implies that x has to be trapped between 5 and -5. Right? So I have this interval of convergence between -5 and 5. Well, that's my interval of convergence, which is I. And so I can write that down in a moment. I'll have to check the endpoints, but again, it's strictly geometric, so it should not converge at the endpoints. We'll check and see, and I'll prove to you, in fact, that they do not. But because it's strictly geometric, these should stay strict inequalities. And then our radius of convergence, of course, is 5, because from -5 to 5 is 10 wide, and half of that is 5. So our radius of convergence is 5. Now, I said the interval of convergence, because it is strictly geometric, should definitely be open -5 to open 5. Now, if you weren't sure, you can always check it and determine that that's true. But because it's strictly geometric, we know that this is always strictly less than 1. That's the condition for convergence of a geometric series. So you could be done with this problem right now. But if you're not sure and you want to establish that for sure it doesn't converge at those endpoints, you could check the left endpoint and the right endpoint. So check left, check right. Now, is it required on this one? No. This one can be written as a strictly geometric series. We know the inequality will remain strictly less than. We're essentially done. But let me show you the process for checking. Coming back to the original to the original series, and I'm going to get that copied. Let's hope this doesn't freak it out. So let's move this down a little bit. And we'll paste that here so we can, so we can see it. All right, so that's our original series. And I want to check the left endpoint -5 and the right endpoint 5. So if I take those values and I substitute them into the original series, which in this case would be a negative times -5 over 5 raised to the nth power, this would give me, of course, basically, well, a double negative gives me a positive, and 5 over 5 is 1. And this gives me the series from n equals 0 to infinity of 1 to the n. Now, if n is a finite value, then this is just the series of 1, which becomes the series from n equals 0 to infinity of 1. But the limit of that sequence is 1. The limit of the sequence is not 0, so it diverges by the divergence test. Now you can take a look at the right endpoint, doing the same process and substituting the value of 5 in place of x. And then you get -1 raised to the nth power. Now for this one, you might actually want to write out some of the terms so you can see what the pattern is. When n is 0, you would get a positive 1. And when n is 1, you would get a -1, then a positive 1, then a -1, then a positive 1, then a -1, and so on. So it's alternating between 1 and -1. Well, if I look at the two sequences, I can take the sequence of the odd terms, which all go to positive ones. Those go to 1. And the sequence of all the even terms, that goes to -1. And since the limit of the two sequences is not the same, then the limit of the sequence in general does not exist, which means it's definitely not 0, which means, again, it diverges by the divergence test. So again, we proved in this case that simply using the strict inequality from the geometric series does work. You can always double check, but again, if it can be written in strictly geometric form, you shouldn't have to. It will stay a strict inequality. When you apply the ratio test, though, you do always have to check the endpoints for convergence. Let's now take a look at the next example, which is example number 2. I'm going to eliminate these 2 lines. So let's take a look at this one. Now, this one is much more complicated than the previous one. And I've got this negative times 3 to the n, and I've got an n plus 1 in the denominator. So even if I could get them all written together raised to the n or n plus 1 power, there's no way for that base to not depend upon n, which means that this cannot be written in strictly geometric form. And you can write out several of the terms of the series, and you'll see right away that moving from one term to the next, you're not always multiplying by the same thing. So then you know it can't be written in geometric form. And that's my hint right here. It cannot be written in strictly geometric series form. So what we want to do instead is we want to apply the ratio test. So when we look at this one, to apply the ratio test, we want to first see if there's something we can do to maybe simplify this a little bit. All right, so we've got a 3 on the outside and a -3 to the n on the inside. Now I want you to be very careful with your algebra here. We can pull the 3 inside, and that will give us the series from 0 to infinity of 3 times a -1 times 3 to the n, x to the n plus 1 over n plus 1. That negative is not a part of the base. It's not in parentheses with the nth power outside. So it has to be interpreted as -1 times 3 to the n. Well, then I can take the 3 to the first times 3 to the n, and I can then rewrite my series, my power series, since I have x to the power n plus 1. I can rewrite this now from 0 to infinity as -1 times 3 to the n plus 1, x to the n plus 1, all over n plus 1. And again, there's no way to get this written as just a single constant multiplied by some r that doesn't depend on n raised to an n or n plus 1 power. It's not possible. So it's not strictly geometric, so I'm going to apply the ratio test. So now I'm going to be looking for rho, which is the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n. Now, to do this, I'm going to have to rewrite my series. So I've got a -1 times 3 to the n plus 1 plus 1, x to the n plus 1 plus 1 over n plus 1 plus 1. Again, we're replacing n with n plus 1. And then we're going to divide this by the original, which had, I need to extend my absolute value, -1 times 3 to the n plus 1 power, x to the n plus 1 power over n plus 1. You could also have manipulated the subscript. Here, the lower index of summation, you could have pushed this forward by 1, back that up by 1, and then you would have slightly less complicated powers to be dealing with. Either way works. So when we're looking at this one, I need to go ahead and work out what these powers become. So over here, I have the limit, n is going to infinity, and I have an absolute value. Notice that since I have the negative ones inside absolute values, I can drop those. They're going to go away. And 3 to the n plus 1 plus 1 becomes 3 to the n plus 2. And then I have x to the n plus 2 divided by n plus 2, all divided by 3 to the n plus 1 times x to the n plus 1 over n plus 1. Now I can simplify this further. Notice that I've got one more 3 up here. So again, we do what we've done before, and we sort of back down the higher power until it matches the lower power. So I've got 3 to the n plus 1 times 3, that gives me 3 to the n plus 2, times x to the n plus 1 times x, that gives me x to the n plus 2, all divided by n plus 2, multiplied by the reciprocal of the denominator, which is n plus 1 over 3 to the n plus 1 times x to the n plus 1. Now, when I do that, the 3 to the n plus 1s will cancel, the x to the n plus 1s cancel. And then I'm left with the limit as n goes to infinity of 3x times n plus 1, the quantity, divided by n plus 2, the quantity. Now, the 3 is definitely a constant, which can be pulled out, but notice that the variable x is also a factor, and it doesn't depend on n, it's x to the first. So it can also be pulled out, but the x, when it comes out, has to stay in the absolute values. The 3 does not, but the x does. So this then becomes 3 times the absolute value of x times the limit as n goes to infinity of the magnitude of n plus 1 over n plus 2. Now, since n is starting at 0, we know that, in fact, we can now drop those absolute values. This has form infinity over infinity. We know we could apply L'Hopital's rule, but by now you've done this one so often that you should know that the limit of that is 1. So that means that the value of rho from the ratio test is equal to 3 times the absolute value of x. Now, when does the ratio test give you a convergent result? When the value of rho is less than 1. So we're going to take rho and we're going to set it less than 1. So this means that basically we have the absolute value of x, isolating that variable in the absolute values, less than 1/3, which means, of course, that it's sandwiched between 1/3 and negative 1/3, or rather the other way around, if you want to do it in number line order. Now, again, we've used the ratio test, so we're going to have to establish what happens at negative 1/3 and at 1/3, because it could be something other than what we originally started with. So it's not for sure that those are going to converge there. So we're going to come back to this one. Let's see if I can get the whole thing copied off. All right, so we're going to copy this and we're going to paste it down below. All right. And I'm actually going to move it up here a little bit. Okay, so I need to check the left endpoint and check the right endpoint. So I'm going to check my 2 endpoints. Now, I already know what the radius of convergence is going to be. It's going to be half of the length of this interval. So the radius of convergence has to be 1/3. So that much I know already. I know that it converges for sure in the open interval, but I don't know about the endpoints. So I'm going to check the left, and I'm going to substitute that value in. So I get n equals 0 to infinity, -1, 3 to the n plus 1 times, and I'm going to substitute -1/3 to the n plus 1 over n plus 1. Well, what's that going to do? Well, I've got 2 things raised to the n plus 1 power, so I could put those 2 together, and that would give me 3 times 1/3, which would give me a -1 to the n plus 1. So this would give me the following: n equals 0 to infinity of -1 times -1 to the n plus 1 over n plus 1. Now, if you're looking at this, isn't this going to alternate in sign? In fact, let's go ahead and manipulate the subscript. If I manipulate the subscript and move it forward by 1, I've got to move the power back by 1. Doesn't this become the series from 1 to infinity of -1 times -1 to the n over n? Other than the -1 to the first power, this is the alternating harmonic series. We know the alternating harmonic series converges. So when we're looking at this particular one, this must converge by alternating harmonic series. It is the alternating harmonic series. So we know it converges at -1/3. Well, what about at 1/3? We don't know what happens at 1/3. Let's take that one and let's find out what happens there. So I'm creating some more space here. So now I want to check the right endpoint by doing the same thing. I want to substitute the value in. So I'm going to check the right. Okay. Probably need a little more space here. So I'm going to check the right. So I'm going to substitute in the series n equals 0 to infinity, -1. And let's go ahead and put the 3 and the x in parentheses. So I have 3x to the n plus 1 over n plus 1. Make it a little easier. And I'm going to substitute in place of x 1/3. So I have -1 times 3 times 1/3 to the n plus 1 over n plus 1, which gives me the series n equals 0 to infinity of -1 times 1 to the n plus 1 over n plus 1. And then I can manipulate the subscript again. And I can start this one at 1. And this becomes the series from n equal 1 to infinity of the constant -1 multiplied by 1 to the n over n. Now 1 to the n is, of course, the value of 1. It's not alternating, so it's always just 1. So we get n equal 1 to infinity of -1, a constant, times 1 over n. Now this is not alternating because this -1 is not raised to a power. In fact, we could pull this on the outside provided that this converges. And when we're looking at this, this is, of course, the harmonic series, which we know diverges. So this is the harmonic series. And it diverges. So then we are going to say that our interval of convergence, which is I, is going to go from closed -1/3, where it gave us the alternating harmonic series, which converges, to 1/3, which gave us the harmonic series, which diverges. Okay? So in this particular case, we had to apply the ratio test because we could not write it as a strictly geometric series. And because of that, we had to check each individual endpoint. We found that it converged at the left endpoint, but not at the right endpoint. Let's take a look at another example. In the next example, we have example 3. We have, again, a representation for a power series where there are factors that depend upon n that cannot be rolled into a common ratio. So we have n to the 20th power, and we have 2n plus 1 quantity factorial. So to get from one term to the next, we're not always multiplying by something dependent only on x. So in this case, we cannot represent it as strictly geometric. And since we can't represent it as strictly geometric, what we do instead is we apply the ratio test. So, and of course, we could also do the root test, but the ratio test makes more sense in almost all cases. So now we're going to apply the ratio test. So we have rho, which is the limit as n goes to infinity of a sub n plus 1 over a sub n, which is going to be the limit as n goes to infinity of, and we're going to replace n with n plus 1 in parentheses to the 20th times x to the n plus 1 power over, now we need to have 2 times n plus 1 plus 1 quantity factorial. Notice that the n plus 1 has to be in parentheses, and the whole thing is also in parentheses with a factorial outside. And then we're going to divide this whole thing by the original representation of the sequence, n to the 20th x to the n over 2n plus 1 quantity factorial. And this is inside absolute values. We're testing for absolute convergence here. So go ahead and pause the video, work this one out, get a value for rho, and remember that it will converge when rho is less than 1. Find your interval of convergence, your radius of convergence, and be sure that you check the endpoints. So I'm going to pause the video while you go and do that work, then turn the video back on and we'll compare our answers. Let's see how you did. Again, we started with the ratio test. We have a n plus 1 over a sub n. Remember that you are replacing n with n plus 1, so the factorial becomes 2n plus 2 plus another 1, or 2n plus 3 quantity factorial, which is what you see here. And then you can rewrite the x to the n plus 1 as x to the n times x. The x to the n's cancel. Now, the next thing you want to do is you want to get the things raised to the 20th power together, and you want to get the factorials together. So we kind of split things up into the following. So you can see that I've got the expressions raised to the 20th power together, and then I'm going to take n plus 1 over n quantity to the 20th. I've got this factor of x by itself. It's x to the first, doesn't depend on n. So I can factor it out of the limit, but remember, we don't know what x is, so it has to stay in absolute values. Then we can rewrite the 2n plus 3 quantity factorial as 2n plus 3 times 2n plus 2 times 2n plus 1 factorial. Those cancel, and we're left with this expression here in absolute values. Now, because n is starting at 0 and getting larger, well, actually not 0, I guess it's starting at 1 and getting larger, then we know that we can drop the absolute values, but of course it's not wrong to leave them. Now we have the limit of a product. Now limits are the most powerful construct in calculus. So we can split the product and take the product of the limits. And that's the next thing we want to do. So we're going to take the product of the limits, which is the limit of n plus 1 over n to the 20th. And then we can actually, because 20 is a constant that doesn't depend on n, we can pull the limit inside the power, and we can establish the limit of n plus 1 over n as n goes to infinity. Well, we know what that's going to be. It's going to be 1. And so we get 1 to the 20th, which is 1. Now, the limit of the second part, as n goes to infinity, the numerator is a constant 1. The denominator is blowing up, so it's going to drive the expression towards 0. It never actually gets there, but it gets darn close. So this last factor becomes a 0, but we have to make sure that all three factors are finite values. We can't have something indeterminate in there. So we complete this first one, 1 to the 20th, which is 1. So we get the magnitude of x in absolute values times 0, which is going to be 0 no matter what the value of x is. Now, that's our value for rho from the ratio test, but 0 is always less than 1, which means that this converges for all values of x. It doesn't matter what x is. So our radius of convergence is infinity, and our interval of convergence is the entire real number line, negative infinity to infinity. Let's take a look at one more example before we move on to talking about power series and functions. In this particular one, your first instinct might be, well, it looks like I could probably get them together as some common ratio, not dependent on n, with something dependent on n on the outside. But the problem is you've got 2n in the power on x and only 1n in the power on 3. Well, those are way far apart, way far apart. So there's not going to be a way in order to get it written where you have a common ratio not dependent on n. It's not going to happen. In which case, we can't write this one in strictly geometric form. So we're going to have to apply the ratio test. So we're going to apply the ratio test on this one. And again, we are looking for rho. So rho is going to be the limit as n goes to infinity of a sub n plus 1 over a sub n. And this is going to give me the limit as n goes to infinity of x to the 2 times n plus 1 over 3 to the n plus 1 minus 1, all divided by x to the 2n plus 1 over x, or 3 to the n minus 1, all in absolute values. Now we're going to take the denominator fraction, we're going to multiply by the reciprocal, and then we're going to back things down. So this is actually going to lead to 2n plus 2 plus 1, which is 2n plus 3. So then I have the limit as n goes to infinity of x to the 2n plus 3, and then n plus 1 minus 1 just gives me n. So divided by 3 to the n. And then I'm going to multiply by the reciprocal of the denominator, 3 to the n minus 1 over x to the 2n plus 1. Now, clearly 3 to the n is larger than 3 to the n minus 1. So I'm going to write this one as 3 times 3 to the n minus 1. X to the 2n plus 3 is 2 larger than this. So I'm going to pull 2 of these off and have x squared times x to the 2n plus 1 again. So this leads to the following expression. N approaching infinity, x squared x to the 2n plus 1 over 3 times 3 to the n minus 1 times 3 to the n minus 1 over x to the 2n plus 1. Now we can do the cancellation. So we've got cancellation of 3 to the n minus 1 and x to the 2n plus 1. And this will lead us to another expression. Now, the x squared does not depend upon n, so we can pull this out and pull it to the front. So we have the absolute value of x squared, which of course is going to be strictly positive no matter what. So we could technically drop those absolute values. And then what's left is just the absolute value of 1/3. All right, so I've got a 1/3 there. Well, what is that going to tell me? Well, this limit of a constant is just the constant. So I get 1/3 magnitude of x squared for my value of rho. And I know that this will converge provided it's less than 1. So again, I'm going to do the same kind of thing. And I'm going to move the 3 to the other side. So I'm isolating that absolute value. And so this gives me that the absolute value of x squared, looks like I've got my absolute values on the wrong side there, should be less than 3. Well, now I'm going to take the square root of both sides. And of course, I could drop the absolute values. And I could just instead write x squared less than 3, which means that it's got to be between the negative square root of 3 and the square root of 3. So I've got these two values, one on either end. Now, this came from the ratio test, so we have to check the endpoint. So we're going to check the left endpoint and check the right endpoint in the original. So we're going to come back up here to where we have the original, which we can see is right here. We're going to copy that off and paste it down below. And then we're going to plug in each of the left and right endpoints, negative square root of 3 and square root of 3. So go ahead and pause the video, work that out, and then turn the video back on and tell me what you got for the interval of convergence. So let's see how you did. Remember that what we found was that the basic interval of convergence is between negative root 3 and root 3. But because it came from the ratio test, we have to test the endpoints. Now, when we take a look at testing the endpoints, we use the original series again, which is this one right here, and we substitute the value of the left endpoint and the right endpoint in one at a time into the original series in place of the variable x. Then we have to determine, using all of those convergence tests from the first chapter, that would be the divergence test, the integral test, limit comparison, comparison test, alternating series test, all of those tests in order to determine whether or not it converges at the endpoint. So in doing so, we first substitute the left endpoint, negative root 3, and then we have to do a lot of algebraic manipulation. Notice that this consists of two constants, negative 1 and root 3, both raised to the 2n plus 1 power. So we can split those up and represent them in this way. Then the square root of 3 can be written as 3 to the 1/2 power. Now, the reason I want to do that is I see 3 to a power in the denominator. So if I can get this factor written as 3 to a power, then the bases will be the same and I'll be able to combine the exponents. So when I have one base to 2 powers, the 1/2 power and the 2n plus 1 power, I multiply the 2 powers together, and that will give me n plus 1/2. Then I've got two factors, both base 3, divided by each other. So I take n plus 1/2, the numerator power, and subtract n minus 1 from it, which is what you see here. with the -1 to the 2n plus 1 just hanging out. That's going to alternate the signs. This gives me 3 to the 3/2 power. Now, the -1 to the 2n plus 1 just alternates the signs, but because the rest of the sum end is a constant, it's basically the square root of 27, then this limit of this sequence does not go to 0, so it diverges by the divergence test, which tells us we'll have an open interval on the far left side. Then we can look at doing the same thing on the right side, but notice the only difference we're going to have is we're not going to have this negative, so we don't have the -1 to the 2n plus 1, but otherwise it's exactly the same as the one that we just did. And it will lead to the sequence 3 to the 3/2, or 27, the square root of. And because the limit of the sequence doesn't go to 0, it diverges by the divergence test. Usually checking the endpoints is mostly a matter of checking the divergence test. Not always, but generally speaking, it's either the divergence test and it diverges, or it becomes the harmonic series, which diverges, or the alternating harmonic series, which converges, or a p series. And then, of course, if p is greater than 1, it converges. If p is less than or equal to 1, it diverges. So because of this, we know that we have the radius of convergence to be the square root of 3, and the interval of convergence to go from -√3 to +√3. Now what we want to do is we want to take a look at power series and functions. We want to see how we can define some functions using power series, because being able to represent a function with an infinite polynomial would be a pretty powerful tool. Why? Because polynomials are the easiest functions to analyze. They're easy to differentiate, they're easy to integrate. They only involve the operations of addition, subtraction, multiplication, and division. So if we can represent some complicated function with one of these infinite polynomials, then we could use the polynomial representation to take the derivative or to integrate it, and that might be easier. We could also, in fact, use a finite number of terms from the infinite series to approximate values of the function. So we could maybe take the first 12 terms and use that to approximate the value of the function at some value of x. So the question becomes, when can we represent a function by a power series? Now, remember that for each individual power of x inside the interval of convergence, the power series has at most one value. So we can kind of think of that as a function. For each x in the interval of convergence, I get one value out for the value of the series. So 1x, one value of the series, 1x, 1y. That's a function, basically. Every x has one y value. So we can think of the value of the series as being the result of substituting the value x in. Now let's think again about the example that we just did, which was example 4, and we found it to converge on open -√3 to √3, also open. Now the number x = 1 is in that interval because 1 is between -√3 and √3. So if I were to take the original power series, which we've represented here, it must converge to some unique value when x is 1. So what I've done is I've taken the original power series and I'm taking an x value in that interval of convergence and I'm substituting it in place of the variable x. Now this is going to give me, in this particular case, 1 to the 2n plus 1, but n is a finite value. It's going to infinity, but each n individually is a finite value. So 1 to that power just gives me 1. Well, I can rewrite this as 1/3 to the n-1 power, which means that this is a strictly geometric series where the common ratio is 1/3, and the first term becomes 1/3 to the -1, which is 3. So then I get 3 over 1 minus 1/3, or 3 divided by 2/3, which is 9/2. So when the value of x is 1, the value of the power series is 9 halves. I know, it just kind of blows your mind. So this is representing some function. If we used a different value for x in the interval of convergence, we'd get a different value. Now let's take another look at the basic geometric series 1 plus x squared plus x cubed, which is the series from 0 to infinity of x to the n, and compare it to a geometric series a plus a times r plus ar squared plus ar cubed, and so on. We know a first in the second series is a, and the common ratio is r. So we know that this one will converge to a over 1 minus r. All right, and it will converge provided that the common ratio r is between -1 and 1. Now, if we use that idea to represent the other one and compare it to the other one, then we know that it will converge, the first one, as long as the magnitude of x is less than 1, and it will converge to its first term divided by 1 minus its r. But its r is the variable x, and the first term is 1. So it converges to 1 over 1 minus x, which is a function. So on the interval of convergence, this series converges to a function 1 over 1 minus x. And we can write this in this format. So this is equal to 1 over 1 minus x, provided x is between -1 and 1. Okay? So we're representing the entire power series with an actual function. Right? And we're looking at it only over the interval of convergence. And that's not true outside of that interval of convergence. So then what we want to do is we want to look at some approximations for this particular value. So in this case, we're letting s sub n be the sum of the terms up to that power. So S2 is the first 3 terms, actually. It's 1 plus x squared, where the power matches the subscript. That's not the normal way that we define S sub n, but how you define S sub n is kind of arbitrary. You can do it either way. So either the 2 marks the first 2 terms, or the 2 marks the highest subscript value. So it can be done both ways. So we have S sub 2, S sub 3, S sub 4, and so on. And over here, you can see in this picture, we have the interval between -1 and 1, which is from here over to here. And the actual function, 1 over 1 minus x, is here in this dark blue color. And we can see that S2, S4, and S6 are relatively close to that graph when I'm on that interval between -1 and 1. And the higher I go, the more terms I take, then the more accurate it gets over a longer interval. So you can see that S2 kind of veers off about here from the graph of 1 over 1 minus x, but S sub 4 takes a little bit longer, has a wider interval over which it's a good approximation. And S6 has an even wider interval over which it's a good approximation. So we can see in this way that we can approximate the power series in these various ways. Now let's take a look at the function 1 over 1 minus x squared. This can also be represented with a power series. It also has an interval of convergence of -1 to 1. When we look at this one, again, going from -1 to 1 on the real number line, we can see that the actual function 1 over 1 minus x squared is again in this blue color. And then we have the 3 functions, S2, S4, and S6, which are approximations of the infinite series. And they're better and better approximations for that function over wider and wider intervals, only between -1 and 1. Now, outside of that, they probably veer off wildly from that function. Let's take a look now at example 5. What we want to do is we want to use the geometric series pattern where the series of x sub n converges to 1 over 1 minus x to find a power series representation for a different function. So this is x cubed over 1 minus x. This also has center of 0, and we want to find the radius and interval of convergence for these. So what do you think that you would do first in order to find a new power series representation for it? Well, the first thing we want to do is we want to represent the new function g in terms of f of x, because we know what that series looks like, and we know that it converges to 1 over 1 minus x on its interval of convergence. So what we want to do then is we want to rewrite g of x, which is x cubed over 1 minus x, instead as x cubed times 1 over 1 minus x, which is basically x cubed times the function f of x. So then we should be able to write instead the series of x cubed times the series n equals 0 to infinity of x to the n. And x cubed does not depend upon the subscript n, so we can pull it inside the series. And this will give us the series of x cubed times x to the n. Now, the bases are the same. They're both x, so we can combine them together and represent them with the base x and the power x or n plus 3. So this gives us x to the n plus 3 power, which looks an awful lot like a geometric series, and in fact it is. We can again manipulate the subscript. We can subtract 3 here and add 3 here to compensate. This is the same thing as the series from n equal 3 to infinity of x to the n. And we know again that in this case, the common ratio is x, which doesn't depend on n, so it can be written in strictly geometric form, which means that it must have the same interval of convergence as what we've had before. So this is going to converge, in other words, when the magnitude of x is less than 1, or when x is strictly between 1 and -1. So when we're looking at these, then we know again that this must be the interval of convergence. So we have the interval of convergence as -1 to 1, since it was written in strictly geometric form, and the radius of convergence is 1. And we can represent it either in this form or in this form here. They both will represent x cubed over 1 minus x. So this power series here and here represent that function. Let's take a look now at example 6. So in example 6, we have a similar problem, but this one is much more complicated. Getting it in the right format is more complicated. We have a function 1 over 1 plus x squared. Now, that is not matching the geometric form. So in order to make it match the geometric form, remember that ordinarily what I have is some h of x equal to 1 over 1 minus x equal to the series from 0 to infinity of x to the n, all right? That's the normal geometric series pattern, the normal power series pattern. So what we try to do is we try to make this one match that pattern. The first thing you have to do is make sure that the constant in the denominator is a 1. If it's not a 1, divide by it. Then we have to make sure that we are subtracting the variable term. So instead of writing plus x squared, I write minus a negative x squared. That then puts it in this 1 over 1 minus something with the variable pattern that we see up here in blue. So then I simply take what that variable expression is, which is negative x squared, and I replace the x in the power series form with that representation. So I have negative x squared to the n. Now I know it will converge under the same conditions, which is basically that that base is less than 1. And this will give me a power series representation for it. So let's go ahead and start doing this work. So I hope that you followed why this has to be true. And we want to use that information now to find g of x, which is x over the quantity 1 plus x squared squared. Now this cannot be written in that form. We have to have a constant on top and 1 minus something with the variable. We have a 1, but it's inside the square. So we don't have the 1 outside minus something with the variable. So we can't write it in that form, but we can take this one and we can do something to it by either integrating or taking the derivative to try to develop it. So what we want to do then is we want to look at the original function f of x, which we know is this power series, and we want to see what we need to do in order to produce g. What's the relationship between f and g? Well, it turns out, let's go ahead and take the derivative. So when we take the derivative of f, this is the derivative with respect to x, and instead of writing 1 over 1 plus x squared, I'm going to write 1 plus x squared to the negative 1 power. It just makes it easier to take the derivative. So we apply the power rule, negative 1 plus x squared to the negative 2, chain rule, times 2x. And then I can drop the power part back to the denominator. So I get negative 2x over 1 plus x squared quantity squared. Now this looks a lot like g, but g only has x in the numerator, not negative 2x. So I can think of this instead as negative 2 times g of x. So the relationship between f and g is that f prime is negative 2 times g of x. Or in other words, I can rewrite g of x now in terms of f prime. So g of x, which is what I'm trying to find the power series representation for, has to be a negative 1/2 times the derivative of f, right? So, but I know what the derivative, or I know what f is. F is this power series representation that we see up here at the top. So then what I want to do is I want to go ahead and write the power series representation with the derivative. So this is going to be equal to negative 1/2 times the derivative with respect to x of the power series representation for f, which was, if I can find it again, the sum from 0 to infinity of negative x squared to the n. And again, that applies for negative x squared, the quantity less than 1, which is basically, again, going to come out to be between negative 1 and 1. So what do you think I can do now? I know this looks kind of crazy. You're like, you're not really going to do what I think you're going to do. And the answer is, yes, I am. This is the derivative with respect to x, and this is x raised to powers. Now I've got 2 powers on the x. I've got the second power and the n. The negative is a negative 1 times x to the 2. So this is the same as negative 1 times x squared to the n. So I can rewrite that then. This is my g of x still, equal ... equals negative 1/2 times the derivative with respect to x of the series from 0 to infinity of negative 1 to the n times x to the 2n. Remember, when you have 2 powers on the same base, you multiply the powers. So it becomes 2 times n. And then I can take the derivative with respect to x because I pulled the constant negative 1 to the n off. And when I take the derivative with respect to x, I know it looks kind of weird. You're like, is that really allowed? And the answer is yes, it is allowed. And so we end up with negative 1/2 the series, negative 1 to the n And then we have 2n x to the 2n minus 1. In other words, I move the derivative operation inside the series, which is allowed. I'm allowed to do that because it doesn't depend on the subscript variable, which is n. And then I can rewrite this one. So I have this 2 and I have this 1/2 on the outside. So I can pull the 1/2 times the 2. Those will cancel. And I have another negative. So I could make it -1 to the n plus 1. So I have this series n equals 0 to infinity of -1 to the n plus 1 times n times x to the 2n minus 1. So this is now a representation of that particular power series. And when we're looking at this power series, if we want to know whether or not it converges, we know that it must converge according to the rules that we've had before, and we can find the interval of convergence. So to find the interval of convergence for this one, we can again apply the ratio test. So if we apply the ratio test, we take rho equals the limit as n goes to infinity of the magnitude of an plus 1 over a sub n. And I'll let you go ahead and work that out. Pause the video, turn it back on when you've got that worked out. So again, after we made our substitutions, we got the power series representation for the function as -1 to the n plus 1 times n times x to the 2n minus 1. Now, because of the n factor, we can't write it as strictly geometric, so we apply the ratio test. And hopefully after you applied the ratio test, you came up with rho equal to x squared, which again, you can drop the absolute values since something squared is always strictly non-negative. Now this will converge provided that rho is less than 1, which is the same condition for convergence as we have on the geometric series. So we know it will converge between -1 and 1, but we have to check the endpoints coming from the ratio test. So we check the left endpoint. Now we have to do some algebraic manipulation here, lots of power rules. So we have -1 to the n plus 1 times n times -1 to the 2n minus 1 power. And then we have the same base -1, so we add the powers, and that gives us -1 to the 3n times the factor n. Now you can split that up as -1 cubed to the n, and -1 cubed is -1. So you get -1 to the n times the factor n, but the limit of that sequence does not go to 0 as n goes to infinity, so it diverges by the divergence test. The right endpoint is actually a little bit easier to check. On the right endpoint, you're substituting 1 in place of the variable x. So we have -1 to the n plus 1 times the factor n times 1 to a finite power, which is just 1. So we get -1 to the n plus 1 times the factor n, which diverges by the divergence test. The limit of that sequence does not go to 0, so it has to diverge. And that tells us that the interval of convergence is from open -1 to open 1, and the radius of convergence is 1. Let's now turn our attention to another example, example number 7. In example 7, we again want to take advantage of the typical power series representation, x to the n, representing the function 1 over 1 minus x, provided we're between -1 and 1, to find a power series representation for g of x, which is 3 over 3 plus x with the same center 0. And then we want to find the radius and interval of convergence for the new power series, which will represent 3 over 3 plus x, using this one as our guideline. Now, in order to do that, we want to get this to look like this format. So we don't need a derivative, we don't need to integrate, but in this case, to get this to look like that, I need a 1 as the constant in the denominator minus something with the variable in it. So that's the first thing I do. I go after that 1 in the denominator. So I'm going to take what I started with, which is g of x, and I'm going to find its relationship to f of x. So I've got, pull off the 3 in the numerator. Well, I guess we could leave it for a moment. First, we want to take this 3 in the denominator, and we want to make this 3, let me highlight it, this 3, we want to make that one be a positive 1. So I'm going to multiply by 1 in the form of 1/3 over 1/3. Now that will give me a 1 in the numerator, a 1 for the constant in the denominator, which is what I was after, plus x divided by 3. Now I'm close to the format for f. I've got the 1 in the numerator, I've got the 1 in the denominator, but I need minus something with the variable in it. So I do a double negative. So this can be written as 1 over 1 minus negative x over 3. And now it's written in the same format as f. So I can write the power series representation, substituting negative x over 3 in place of x. So this then becomes the following power series from n equals 0 to infinity of negative x over 3 raised to the n. Now this one is written in strictly geometric form. The common ratio is negative x over 3. It does not depend upon n, and it's being raised to the nth power. So no, it's got to follow the rules for geometric series. You can always plug them in and check. But in this case, since it is strictly geometric form, we don't actually have to do that. We know that this is going to converge to that expression for g when the magnitude of negative x over 3 is less than 1. Now we can drop the negative and we can pull the 3 out and move it to the other side of the inequality. And this, of course, happens when the magnitude of x is less than 3, which basically tells me that it's going to converge between negative 3 and 3. Again, we don't necessarily need to check the endpoints or check convergence with the ratio test, because this one can be written strictly in geometric series format. And so we know that it must converge and that it must be strict inequality. So essentially we're done. We have the interval of convergence, negative 3 to 3. We have the radius of convergence, which is 3, right? So now we have one more example that we want to look at before we end this video, and that's example number 8. Example 8 is a little bit more complicated. It's more like the one where we had to take the derivative, but in this case, we're not going to be taking the derivative, or yeah, I think we do take the derivative, but we actually end up integrating in the power series. So the problem is our g of x is not even remotely in the format of f of x. I can't even get it close to that. So I have to look at the expression for g of x, which is a natural log function with the argument 1 minus 3x. And I have to think, well, what could I do to natural log to make it look like something 1 over something minus something? How can I get that? Well, I could take the derivative of natural log. So if I take the derivative of g of x, can I represent it in some way that it follows the format for f of x? So what I want to do then is I'm going to start with g prime of x, which is going to be 1 over 1 minus 3x times a negative 3, which basically gives me negative 3 over 1 minus 3x. Now, how can I make this into the format that matches f of x? Well, I could pull the negative 3 out to the front. I've got the 1 in the denominator and I've got a minus. I don't want to mess those up. So I can pull the negative 3 to the front, and I can represent this one then as negative 3 times 1 over 1 minus the quantity 3x. So now it looks like the format for f. So this must be the same as the power series multiplied by negative 3 with 3x replacing the x. So this becomes negative 3 times the power series, n equals 0 to infinity. And replacing x, I have 3x. right? So I get this expression right there. Now, what do I want to do from this point on? So I'm looking at this one right here. I've got this 3x to the n, and I've got a negative 3 on the outside. So the question is, does this follow geometric series form? Well, if I take a look at this is not G, this is G prime. This does follow geometric series form, all right? So far it does, but the problem is it's not G, it's G prime. So how can I get from G prime back to G? Well, to undo the derivative, you integrate. So what we want to do now is we want to integrate G prime of x with respect to x, and then we will want to integrate this negative 3 times the series of 3x to the n. Now, in order to integrate the series 3x to the n, I know the negative 3 is a constant. I can just pull that to the front. I could even push it inside the series if I want to. I've got to separate this 3 and this x apart because the 3 is a constant, and I want to go ahead and figure out what the powers are without having them combined together. So the next thing I'm going to do is I'm going to rewrite this, and I am going to push the negative 3 on the inside times 3 to the n times x to the n. Now, the negative 3, I can think of as negative 1 times 3. So I can actually think of this as a negative 1 times 3 to the first. Then I have 3 to the first times 3 to the n, which is 3 to the n plus 1. So I hope you can see where I'm going with this. This, of course, is going to give me g of x. So I get g of x equal to, and now I've got the integral with respect to x. I should put that on here, dx. The integral with respect to x of the series from n equals 0 to infinity of negative 1 times 3 to the n plus 1 times x to the n with respect to x. Now, the only thing we're going to integrate with respect to are things that depend on x. Everything else, as far as the integral is concerned, is a constant. So this negative 1 is a constant. This 3 to the n plus 1 is a constant. It only wants to integrate the x to the n. So we can pull the integral inside of the summation, and we have the summation. The negative 1 and the 3 to the n plus 1 are considered constants for the integral, and we get x to the n dx. And then we can apply the power rule. We know what that does. And this gives us the series from n equals 0 to infinity of negative 1, 3 to the n plus 1 times x to the n plus 1, add 1 and divide by the new power. Now, normally we would have a constant, but we don't mess with the constant when we're looking at power series. So we have this right here. We can always add a constant, right? It's not going to be a problem. So we have this expression right here. So what do we do now? Now that we've come to this part right here, this is our new power series for the function g of x, which is the natural log of 1 minus 3x. So I'll write that over here so we can remember what g of x was in the first place. Natural log of 1 minus 3x. So what we're saying is this is equal to the natural log of 1 minus 3x, but only on its interval of convergence. I need to find that interval of convergence. So this is equal to that on the interval of convergence. Now, this cannot be written in strictly geometric form because of the factor n plus 1 and also the factor 3 to the n plus 1. No matter what I do, those are going to, well, actually, I could pull the 3 and the x together, and that would be 3x to the n plus 1. That would be okay. But I can't do the n plus 1. These are not representing a series where you multiply by the same factor to get from one term to the next. It is similar to that, but it is not that. So what I'm going to have to apply is the ratio test. So I'm going to pause the video here, go apply the ratio test, find your interval of convergence, check the left endpoint and the right endpoint, then turn the video back on and let's compare answers. Okay, let's go ahead and compare our results here. So we got this expression right here, and even though we could combine the 3x raised to the n plus 1 power, which matches a geometric series format, the factor n plus 1 does not. So it can't be written as a strictly geometric series. So we have to apply the ratio test. So we apply the ratio test here. Be very careful with your powers. Make sure that in the numerator, you're replacing n with n plus 1. Now, once you work that out, you should have ended up with rho equal to 3 times the magnitude of x, which we know will converge for the ratio test as long as the value of rho is less than 1. So we can divide by the 3, which gives us magnitude of x less than 1/3, or between -1/3 and 1/3. But because this came from the ratio test, it's possible that it converges at one or both of the endpoints. So we're going to rewrite the series right here. And I chose to go ahead and combine the 3 and the x into one base with the common power n plus 1 on the outside, just to make the substitution a little bit simpler. So we're going to check the left endpoint first, which is -1/3. And you'll find that when you substitute it in, you get -1 to the n plus 1 power. Now we can manipulate the subscript to start at 1, and that gives us a negative times -1 to the n over n, which is basically an alternating harmonic series. And so we know it has to converge there, which means we'll use a square bracket on the left endpoint. When we check the right endpoint, we're going to get essentially the same thing, but instead of having -1 to a power, we have +1 to a power. Now, 1 to a finite power is just 1, and so we get -1, but not raised to a power over n plus 1. Again, we can manipulate the subscript, and we can write this as a constant over n, which is basically a multiple of the harmonic series. The multiple is -1, which we know diverges. And so our interval of convergence then becomes closed -1/3 to open 1/3, and the radius of convergence is 1/3. So for any value of x in here, or x equal to -1/3, I can then represent the function that we had at the beginning. Oops, I went to the wrong problem. There we go, g of x, which is the natural log of 1 minus 3x. I can represent that with the power series that we got for it, which of course is this one that you see here. I know that power series are rather difficult when you first start working with them, and the problems get very long. You have to be very careful with your exponent rules and your algebra. Make sure that you really have the ratio test down well. That will help you when you're representing functions with power series. Now, in the next video, we're going to be taking a look at properties of power series and some different ways of representing functions with power series. I hope you'll join me for that next video.